We discussed about regression, and we just saw that regressions are basically comes in two flavor. One is your linear and other is no linear. So linear is mathematically tractable, easy, and we can do it. And when it comes to regression, so we discussed that basically, uh, just a minute. This regression we have discussed last class that let's say there is some sort of a function approximation, let's say. So these are sets of inputs are given to us, and this is, and only thing is what is there inside we don't know. So if I take this y and this x1, x2, say xm, so this set of this x is called regressor or the independent variable, and dependent variable what we call the response, right? So basically what we are looking for is how do I find this, or you can say that to y, this kind of function map we are trying to find it out. And we saw that in order to find this, when you go for linear regression, it may be something like this: w1 x1 plus w2 x2 plus say wm xm, whatever. So basically this x1, x2 and xm is anyways, these are the input variable, it is known to you. What is not known is w's, right? W is not known. And then we found that there are two approaches for doing this. Another is, one is MLE and another is MAP. That is maximum likelihood estimate and maximum a priori, this one, posteriori, a priori posteriori, this one. Uh, in using this and this, it is possible to find this values of weights, right? And then we saw it also. And so when you go for MLE, there is maximum likelihood estimate. We don't take prior variable, this one, prior probability of the response, where in case of when we go for more profound estimation of these weights, we go for MAP, right? That we saw. But also there is some problem because in order to have some sort of balance between stability and bias, we have to go for, we saw that MLE is simple to this one, but not profound, but it is also at the same time it is non-biased, is unbiased estimate. Whereas map is more stable, but it is a biased one. That's what we saw last class. Okay. So now what we'll start today is another module in this, and chapter 3 from Hacking. And this is the most beautiful the things done so far, but we'll see. And of course, it will undo many of those things which you might have done in the first year mathematics also. So we'll do this. Don't worry about that. Whatever is there, I'll explain. And these two chapters has been little mathematically rigorous because they are the building or the foundational block for whatever we are going to study later. So least mean square algorithm is basically for this particular chapter, the inspiration is the perceptron. And this chapter or the module serves a basic background or the foundation for the backpropagation algorithm, which we'll talk about the next module, that is under the multi-level perceptron. So backpropagation algorithm, you know that they are the fundamental building block for any neural network system. So we'll see this what least mean square algorithm, or in short LMS algorithm. It's basically a celebrity algorithm, to be very honest with you, especially in adaptive signal processing. We study a lot about this, and it has something to do a great deal of the work in your everybody's mobile phone also. So LMS algorithm, or basically adaptive signal processing part, it plays a significant part over there. So we'll see what all is there in this. So as I mentioned this, the perceptron is the first learning algorithm for solving a linearly separable pattern classification problem. First learning algorithm was there. And so perceptron is perfectly fine if they are something linearly separable and you can classify them. But on the other hand, the least mean square algorithm, which was developed by Whitro and Hoff around 1960, is the first adaptive filtering algorithm for solving problems such as prediction and communication channel equalization. And then you'll maybe thinking why we are studying this map from the 60s, because it is still used and it will be used for further. And this is very interesting. And the idea of the LMS has been inspired by the perceptron, and that we'll see how it is going to be. And this, as I mentioned this, so features of LMS which makes it a distinguished part of it, and why it is still a hero, you can say that. It has linear computational complexity. So very simple it is too. And because linear complexity is there, it's very simple to code and therefore easy to build on whatever the platform you want. An algorithm is robust with respect to external disturbances. When I say algorithm is robust, what I'm literally mean in this scenario or the context is about the condition number. So we'll talk about this, about the condition number, matrix condition number, etc. Uh, I don't know whether you heard about this condition number or not. Has anybody has heard about condition number of matrix or a system? Yes or no? Hello? Okay. So we'll see it at later point of time. I'll explain what do you mean by that. So there are multiple phases of the single neuron system, that is a perceptron. So a perceptron can be act as it can have a different perspective. So it can be used as just a classifier, and the best example is a perceptron. And it can be used as adaptive filter as well as in signal processing. So you'll say that something is used in signal processing, man, why we are studying here? No, you don't have to worry about the applications. What is important is the concepts. So irrespective of the field it is applied. But because was rigorously used in adaptive signal processing, so that's why the application which first comes to mind is adaptive signal processing. So this LMS is basically used for this adaptive filter, and we'll see what is happening over there. So this is basically, if you see this, some sort of unknown dynamic system. Unknown dynamic system is there, and we have output, and here input is there. One simple example I'm quoting here so that you all can get the context and connect with the idea. Let's say mobile phone you are having. Do you think the wireless channel condition remains same always throughout the day? Every second, every minute? Do you understand what I mean to say a wireless channel? Hello? बोलो भाई. Anybody? Okay, I'm wasting my energy shouting on you. So this when I say this wireless channel, what I'm literally mean to say that the ecosystem, the ecological systems we are, the particularly weather condition. So your mobile phone, don't you think that your communication through the mobile phone is get affected by the weather system, or where you are located at that particular time instead you're making a call? So there are many shadowing effect or call drop, etc. happens. Then you say, okay, let me move a little bit here, and whether I'm audible properly or not, or I'm not able to hear you, etc. The slightly you move, and what is happened? You get the signal properly. So basically, what is it that it is unknown dynamic system, dynamic system, and this means what I mean to say unknown, because this weather condition are highly dynamic in nature and it keeps on changing. And so this I'm telling you from a perspective of a mobile phone so that you can get the idea. Now there are certain filters within your mobile phone itself which ensures that you get the signal correctly, and we are able to speak or listen correctly, and there is nobody to tune. You don't say, no, okay, let me tune my frequency or do something like this, and okay, no, you don't do that. You just move here and there a little bit and probably able to catch the signal. So does this adjustment? The moment you change your position or whatever it may be, though basically the weights within the systems get adapted or get changes, and with that particular changes you are able to receive the signal properly, or you are able to send your voice to the other person clearly. So this is what is happening. And for that, so this is the inside story. So do you have black box here? This is unknown dynamic system. We don't know what is there inside. You have the output or the response, and here the inputs are there. Now, when you open it up, so basically it's a single neuron system, which I'm talking about. And here you have this activation potential, and these inputs are there or are having certain weights. And as you know, as we have done in perceptron, we are not giving this subscript of the 1, 1 or 1, 2, etc. because there is only one neuron system. So there is no need to mention JI concept here. And here, if you see this particular blue line, activation function, there is nothing mentioned. So basically, it's nothing but the linear activation function. Means whatever is available here is given here as well. So there is nothing like no activation function is there. Activation function is there. It is just a linear. Now, whatever the value calculate from this one, and this value comes out to be yi because there is no other activation function. So vi is as good as yi is as good as vi itself. Now this one and this. So you want to say that, okay, this is the condition and this is the actual output it got it. And the desired output is di, which is known to you from the training set itself. So you find the difference between the two. You find a difference. That's why this, remember that this is signal flow graph. So we have used this particular notation. See, if I see arrow mark and give it to something means whatever gets here, it get multiplied by that. So basically yi becomes is minus yifi. And here once you two signal to come towards a particular dot or point, as for signal flow procedure, we saw the notations. The EI is nothing but the sum of the two. So DI minus YI. So effectively, it gives you nothing but the difference between the two. So this is the difference between the two. It means actual output and the desired output. The difference is nothing but the error. Now this error has to go inside, and just to indicate that weights are changing or has to be changed, this we use this kind of notation, arrow with the among those particular links. So this notation indicates that this weights has to be changed. Now in case of perceptron or a neural network system, we see that these weights are nothing but the synaptic weights. Is there any query here in this diagram? Hello? Is there any query on this diagram? No. Good. So we have certain, we'll say that what is the filtering structure of LMS algorithm. So we saw that diagram perspective. Let's see what is going inside. When I say adaptive filtering problem, so what do we really mean by that? So consider an unknown dynamic system, which you have seen in the previous diagram, that takes m inputs and generates one output. So basically, we are looking for a meso kind of system, means multiple input, single output. Okay. The system can be described by some input output pair. So let's say for training sake we have, so the xi di is there, and there are some n number of examples. Okay, n number of examples, and here each xi basically is m dimensional and de is basically a scalar value. Let's say that. Oh, so this xi or basically x can, these are nothing but is a stimulus which is activating the system. It can arise in one of two different ways. Either this value could be a spatial or it could be temporal. What I mean to say spatial and temporal is this. So m elements of x, that is the stimulus or the input, can originate at different point in space. Different point in space means you can say x1, x2, etc. In this case, we say x is a snapshot of data. Means is suppose if I am talking about three-dimensional, so say 2 in x direction, 3 in y direction, 5 in z direction. So these are the different points in the space, and so that kind of cube it forms, and that what we call a snapshot of data. Also, it can be temporal data. When I say temporal data, so say that m elements of x represent the set of present and m minus 1 previous value. So that's why you say temporal values. You can see it can appear in this way as well. So now the problem we address is how to design a multiple input single output model of the unknown dynamic system by building it around a single neuron. So this is what we are looking for. What should we do? Just so that single neuron we can design around it. So we keep following things in the mind. First one is the algorithm starts from an arbitrary setting of neuron synaptic weights. So we don't know what is there. So because from learning has to happen. So somewhere you would start, somewhere start. So we'll say any random value you can give it. Later we'll see that is there any way that we can start with some intelligent weight assignment initially, and which will speed up the process. So that we'll see at later point of time how we'll do that. Now, this adjustment to the synaptic weights in response to the statistical variation in the system's behavior are made on continuous basis. So point to be noted here, something is saying that adjustment to the synaptic weight, first point, in response to statistical variation in the system behavior. Can you tell me where do you get this information? Statistical variation in the system's behavior. What signifies here? Means where you get this statistical behavior in the system's behavior? Anybody?
Sir, I think if you're comparing the output of the system to some values that we already know, we can check the variation between the two values.
No, actually this part is saying something about the input data, training data you're seeing. So say for example, of course what you said that you are comparing, that has to be example by example, of course. But how this variation will come into picture? Variation will come into picture means you are given a training example 1, got the output, compare with the desired output, whatever difference is there, you going back and changing. Second input you are giving it, got the output, got the desired value, find the difference, got the error, again you change it. So this statistical variation in the system behavior are basically it reflected, or we get this information from the training data. Is it okay? Hello?
Yes, sir.
Yes.
And this we are doing on a continuous basis. It's not one-time procedure till you exhaust your training data. Okay. Now we'll see this. So, and also the computation of adjustment to the synaptic weights are completed within one sampling period. Means what? Means one particular, here sampling period is nothing but your training data. How many 100 you have? So 100 sampling period you can think of. Now there are two important processes in adaptive filtering, and why this word adaptive comes. Adaptive means your synaptic weights are changing as per the input. So that's why you're calling as adaptive. And there is something called filtering. So filtering has to be look into it. Filtering, probably you might have heard of lot of kind of filter probably in the first year. Later you hardly go through your low pass filter, high pass filter, band pass filter, notch filter, band stop filter, etc., etc. So different signal frequency, you design different kind of filter. So here also some sort of filtering structure. But what we are not talking about the frequency. We'll see that what do you mean by filtering process here. So filtering process is computation. Basically in filtering process we compute two kind of signals. First is output Y, means you give the input and in response to that input you calculate the value of I. Okay. And the another one is the error signal. So you have the Y value with you and desired value is already known from the training data set. You find the difference and that difference is nothing but the error signal. Okay. There is another process what we call adaptive process. Now I found the error signal which reflects, of course, as somebody pointed, is a statistical variation. Now it's reflecting by example this value will be different. Now this has to be propagated back or given back. This error is there, it has to be incorporated, because suppose something you do an assignment, etc., and my job is to give you the feedback and this and where you lost your marks. Suppose we have the assignment for 15 marks, you got say 5 or 10. So where you lost the 5 marks or 10 marks or whatever it may be, so it's my job to give the feedback to you. This here you lost and this feedback is given to you. So you found that this is the error, that you are deserving 15 but you got only 10. The error is there, the difference of 5. So it has to be given back to you and you take it in a right spirit and make those corrections so that in future, then for the next test your values are not going to be different. Ideally the error should be 0, but it does not happen, right? And here it definitely it cannot, because the learning process. Now adaptive process involves the automatic adjustment of the synaptic weights of the neuron in accordance with the error signal. Now the main question comes, man, how this error signal comes and adaptive, it makes changes. So we'll see this. So we know that the neuron is linear. Remember that in perceptron, neuron is not linear. It's a non-linear neuron, and particularly it uses a thresholding function. Basically, it uses a one particular model of neuron that is called Mechler-Spitz model in case of perceptron. But here we use a linear neuron, means my activation function is nothing but the linear function, as simple as that. So whatever the output is there, it is same as the induced local field Vi. So Vi is nothing but Wk xk. All these things here. Okay. And in matrix notation, if I want to write, so I just indicates the ith example or ith sample period you can think of. So xtiw, or I could have written wtxt, wtx, that's all. It's inner product, so only t position cannot change, but the variables can switch always. And of course, w will have the same dimensionality, what the dimensionality of x is there. And signal, we know that ei equals to di minus yi. So I can put it across and subtract it also if required. I could have written di minus xti wi, could have written also. Now, the manner in which this error controls the adjustment of synaptic weight is determined by the cost function. Means how it should be, what should be the cost. Okay, the cost function is that, and this, whenever I say cost function, this issue is closely related to something called optimization. Okay, now I'll take a little digression here, and I'll talk about the optimization, not in detail, but in a very broader sense. So let me go to the board and see very carefully, because whatever given in the Haken is very less, and what we are looking for is somewhat more deeper. So let's see this optimization. There are many types, but we'll talk only two. Something called unconstrained, and another is called constrained. Now, what is this? First of all, if I see optimization, what do you mean by that optimization? In general, any one of you?
So with respect to an algorithm, you could say improving the time complexity, etc. In that sense.
Okay. So this optimization is quite generic in nature as a word. So in what context you are taking, the meaning differs, right? And if you're talking about some algorithm analysis you are doing, so you are making certain alterations so that it gets speed up, so time complexity you are trying to optimize over that. In space complexity accordingly you are doing, but in general what we do is that we will try to find the unknown variable which will make that function either minimum or maximum, right? So that particular thing. So this is normally the process in optimization. So I'm talking about mathematical optimization, and this optimization is also called mathematical programming. And the first time you might have got some flavor of this mathematical programming in your probably +2, you might have heard something on linear programming, and in your +2 mathematics, linear programming and simplex method, etc. These things were there. I don't know whether they are still there or not. So now in this, and as I told, there are not only these two types, there are many other types of optimization, convex, etc. But we'll talk about only these two, unconstrained and constrained, simple thing to talk about. Now, what is unconstrained optimization? Now, in optimization, there is something called, there is a word which we oftenly appears, something called objective function, which is in machine learning or neural network is also called as a cost function, or sometime, particularly in machine learning, people call it as a loss function, many things. So basically they try to design the system so that it costs the least in terms of either algorithm is time or space or whatever it may be. So basically we are looking for designing that kind of system. So it has got different name, objective function, cost function, loss function. So don't get carried away by different nomenclature. As long as the idea is clear to you, you don't have to worry about it. Now let's see f of x is there. I'm looking for, this is my objective function, okay, or cost function or loss function, whatever you say that. Whenever there is a statement something like this, Rmax x f of x, Rmax x, this argument of this particular function, that is x, what will be that which will make this function maximum, or it can also be written as like this, argmin with respect to x. If the x is the variable, if some else is there, I can always write. So suppose if for x, so x, y, z. So if I want to optimize with respect to z, I'll write here z, and I could have written this f of x. So here that value of argument which will make this function minimal is that is what we are looking for. So that is the meaning. Now, whenever you see optimization, these are the optimization problem only. So what do you do in this kind of thing? This is function. So what we do in school also we used to do for maxima, minima, take the first derivative and equate to 0. The idea behind this is that if I'm talking about the maxima, let's say, so you know that, let's say, whatever, this is the form which I am saying that, let's say it is f of x, and I'm looking for the point where the maxima occur for this. So you know that the maxima occur for here. Now imagine that there's a peak of the hill, and its small delta point here, what is happening, the slope is 0. And that is the fundamental idea why we always say that for maxima, take the first derivative equal to 0. First derivative is nothing but a slope. So that point in the system where the slope is equal to 0, and that will happen in here, right? So at that particular point, it is not falling over here or there, slope is 0, and that point you equate to 0, and equating 0, solving that particular problem, it will give you that value of x where this maxima occurs, and corresponding to that, when you substitute this x value in f of x, you get the required the maximum value. So this is for the maximum. For the minima, how it occurs in a different setting altogether, whatever may be. So you see that, and here if you see, there is another point here, and there is another point here. So these are basically local maxima 1, local maxima 2, and this is the maximum across all. So this is called global maxima. These are the local maxima. Similarly here, when you see this particular point is the minimus, is the lowest point as compared to this and this, whatever may be. So somehow we were trying to say that, suppose at the if you have something at this kind of shape and you put a ball here, let's say a whichever steel ball or any ball, you just drop it. So it will keep on going here and there, and finally it goes settle down. When it stops moving anymore, it means it has got to the place where the slope is 0. Of course, in negative direction, slope is 0. So normally this is also found by f of x equal to 0, but for the minima. So this is indicating minimum. Now, so this is very straightforward. So whatever the function you want, take the first derivative equal to 0 and solve for this. So this is the simple thing. If you have one or two variable, what if there is a vector or if there is a matrix, then this kind of idea does not work over there. In that case, we use the concept of matrix calculus. Let's say there is f is a function of matrices, many matrices or vectors are there. So in that case, if I want to find this value where the maximum or minimum occurs, what I'll do, I'll take the nabla of this and differentiate with respect to a. And after doing this, equate to 0, and finally find what value of a is going to make this maxima or minima. So this kind of problems are called unconstrained optimization. We are not putting a constraint. that under this constraint only maxima should happen, or under this constraint only minima should happen. Nothing of that sort. For a simple example, if I say that within a year I want to be the richest person in Manipal, the moment I say, I am saying unconstrained optimization means I want to maximize my profit no matter what the means I choose, right? So this is unconstrained optimization example. On contrary, if I say something like this, if I say max f of x such that g of x less than b, h of x less than c, whatever it may be. So you want to this kind of whenever the optimization problem is there, you want to maximize or minimize the objective function subjected to as or such that subjected to these are the conditions. Now if I say I want to be richest person in Manipal in next 1 year following ethical rules or subjected to ethical rules. And so this is, if I say this subjected to ethical rules or subjected to honesty, I'm putting certain conditions across it. So this kind of or constraint across it. So this kind of optimization problem are called constrained optimization. Constraint optimization. Now, solving constraint optimization is not a straightforward task. It's quite difficult, but not impossible, of course. But because you have to talk about the constraint also, right? Now, when you see this and this, which is easier to solve? And one obvious answer will be definitely unconstrained optimization is easier to solve. Now, there is a technique or there is a technique we look for that whether is there any technique which can transform a constrained optimization problem into a unconstrained optimization problem, whether such technique exists. Can you tell me, any one of you? Hello? Is there any technique which can transform a constrained optimization problem into a unconstrained optimization problem? And first of all, be very clear that why we are looking for transforming a constrained optimization problem into unconstrained is the fact that unconstrained optimization is easy to solve. Once the function is there with you and you want to solve it, you just find the derivative equate to 0. Job is done and solve it. That's all. You don't have to worry about anything else. But it is not so simple in case of constraint optimization problem, because you have to look into those constraint also which was stated for that particular problem at hand. So we are look for some technique which if we can transform a constraint optimization into unconstrained optimization. So more on this I talk about when I talk about SVM. But here just an idea, and that is this particular technique is called Lagrange multiplier concept. So this is nothing but Lagrange multiplier. Lagrange multiplier. That will see what is Lagrange multiplier. We'll see. Now, this let me visit this type of constraints are two types. One is called hard constraint. Another is soft constraint. So what do you mean by hard constraint and soft constraint? So see here. If I say maximum f of x subjected to g of x equal to 0, hx less than or equal to 0. So see, whichever constraint is there which has an equality sign, 0 or b or c, here what is equality sign, is called hard constraint, means it has to meet the hard constraint. Wherever constraint is there and there is an inequality less than equal to or greater than equal to, such kind of constraints are called soft constraints. And this is very obvious. You can say that either less than this or equal to this. But in this case, you are not ready for less than this value, gx less than b. You're not ready for that. It has to be equal to b. So there is a hard constraint and soft constraint. Is this clear now? This much is enough for you to jump further and proceed. Any doubt here?
No, sir.
Okay, good. So we'll move next now. And so all these things I explained you, constraint, unconstrained, etc. So this I just formally put it across. So minimize or maximize what would maybe, and not necessarily that only minimization, maximization could be also there. And this we have to use unconstrained optimization, max fx or min fx could be anything. Now this optimization here, we are, as I told you here, that in this case we wanted to look for this E of I, we have to control the synaptic weight. But what is that particular function? How do I define it? So there is a error space is there or error energy is there. So what we'll do is that we are considering a cost function E of W that is continuously differentiable. We have to, this function has to be chosen in such a way that it is continuous differentiable. And you know the continuation differentiable, why it should be, because you want to find this, you want to solve this optimization problem, which will look for the differentiation. And if differentiation does not exist, then you will not be able to solve it. So that's why you have to choose this cost function in such a way that it should be continuously differentiable function of unknown weight vector W. So ultimately we are looking for that, we are looking for this particular, this error E is nothing but is a mapping from the weight space to the weight space to the real space. That's all, some value it is giving. So you give some weight space, the set of weights, and it gives the real value to you. We need to choose W such that adaptive filtering is done in optimal way. When I see optimal way, what is happening, that the error, resulting error will be least, theoretically 0, which is not possible. So it should be least. Now we want to find an optimal solution, say W star, that satisfies the condition that when I found this, when I say W star means the solution of the problem, means what is the unknown vector W. If I substitute that for this cost function, that value should be less than that any other W which is not a solution. This is what it means. And because it is a cost, so we are looking for lesser, that value which is going to minimize my cost. It is not profit. If profit was there, then you have to find that value of W which will maximize your profit. But here loss is happening, so we want to minimize that loss. So we need to solve an unconstrained optimization problem stated as follows. Basically, we are looking for solving this constraint. We want to say that minimize the cost function EW with respect to the weight vector W. So very simple. So this I can simply say argmin W EW. Simple to say that. This particular statement here, this one can be stated formally because we have not put any constraint as such. So we say that argmin W E of W. We want to solve this. And in order to solve this, the technique is straightforward. Take the first derivative equal to 0 and try to solve it. Now, how we are solving is, and that will be different approaches, and accordingly the value of W will be different. So we'll see that what are the various approaches to solve this. So there are many ways to do this. So before that, we'll try to understand means how EI and all this W, how the relation is. Because directly if you see that um, EI is not directly related on W, but how it is indirectly seen. E of I, you know that it is nothing but the difference between the desired output and the actual output. So di minus y of I. Di is as it is. Y of I is nothing but the xt and w. Xt and w. D and x are here. D is fixed because it's part of your training data. X is fixed, part of training data. So what is variable? Only the w, which can change E value. Okay, so you can say that E is some sort of directly proportional to W, or it is dependent on W, you can say. It is not dependent on D, it does not depend on X, but on W only. What is the weight, how we have been chosen. So we want to minimize the cost function E with respect to weight vector W and find the optimal solution W star. It's very common practice in optimization theory that when you find a solution, the optimal solution, write that particular variable as with the star to indicate that it is the optimal solution. Now, the necessary condition for optimality, as I told you, for whatever the argument etc. you want to solve, take the first derivative equate to 0, and whatever the value will be there, that is the value for your unknown parameter w here. And we know that this I have already told you in the last class also. What is this gradient? So nabla is indicating the gradient, which is nothing but dou by dou w1, dou by w2, etc., dou by wm. So each, because here why it is, because E is a vector, not a one value. It's depending on the many aspects. So and W is basically m dimensional, so it has to be derivative with respect to each one of them. So gradient vector of the cost function when I do this, so this is how it looks like. So now a class of unconstrained optimization algorithm that is well suited for the design of adaptive filter. Remember, this adaptive filter is based on the idea of local iterative descent. Now, before I talk about this local iterative descent, let me take a digression and explain you what do you mean by this iterative technique to solve something. Let's say there is a f of x, whatever, and you want to find that value of x which is going to maximize this f. Let's say. And suppose if you plot this, so let's say if you plot something like this, you have say this kind of waveform is coming. So at different point of x, let's say here, you find the slope. Find the slope means you find a derivative. And so different point means when I say slope, you are finding tangent at every point. Sorry, it's not up to scale. Here so you see this and you keep moving. So this is basically, this is the nature or the feature of the gradient vector itself, or the gradient operator, that it will always point in the direction of ascent. Ascent means going up, right? And you keep on doing this process and you come to the peak of that and say this is my value. But in our case, we are talking about the error space. So error will be basically, we are looking for that value of W which is going to minimize this error energy. And for that we have to, this graph should be in a different way altogether. Let's say it is something like this. So at this particular point you take the difference, gradient, and you find, you find this slope. Here you find the slope. Basically slope in nothing but tangent, you are finding tangent, and this will keep on going. And if you say that, okay, this is the global minima, and accordingly it will tell the value, right? So this process is called gradient ascent. This is called gradient descent. Now, why we are saying is a locally iterative approach. Iterative approach because it does not happen in one go. Each and every point you have to find the gradient ascent or gradient over there, and accordingly proceed. So this is iterative of also local because each and every value you are taking over there, and iterative because it is happening multiple times, right? So this is the idea about this gradient ascent and gradient descent. So in this technique, when we talk about adaptive filtering, where entire training set is there and each training example has to be exposed or subjected to the model, and corresponding to that particular training example, whatever the error comes, this has to be reflected back or it should make the changes. Overall, we have to find that value of W which is going to make this system function optimally. Okay. So here, in order to do this, so we'll see that. So what we are looking for is something like this. And as mentioned that local iterative descent. Why descent? Because in our case, we want to minimize the cost function. But if your requirement is to maximize the cost function, then we go for something called local iterative ascent, not descent. Descent coming down, ascent going up. Okay, this you know. So this is what we are looking for to solve this kind of problem. Starting with the initial guess, we are denoting by W of 0. Generate a sequence of weight vector W1, W2, etc. such that cost function E of W is reduced in each iteration of the algorithm as shown by this. It should keep on. So this is the example which I have shown you here. Let's say this was the case, and this basically this is some sort of energy space is there, and here E of W is the value. This point, this point, this point, this point, this point you have. Effectively, it is going something like this. This is just a rough idea I'm giving so that you can contextualize what it is happening. So if this value is there, you're finding energy, and then you're trying to find that value, the next value, updated value, and there is something here, and then again you keep on finding another value and see that. So every iteration, what should happen, the energy or this error function value should be lesser than the previous one. So every time you keep updating the weight so that I keep on correcting the errors, and so that my next value of the errors is reduced, keep on reducing. And that's why this particular thing, that you start from W0 means initially the weight, this error will be maximum. If the error is least or 0, you are lucky, means that the initial vectors of synaptic weights you have taken is such that it is already almost a learned kind of weight, but that may be very rare. So then you find W1, W2, etc. Means these are the what are the weight factors when you substitute. So say that by n plus 1, what it should happen, that if it is learning properly, then this error energy or value should be lesser than the W of n, means the previous state, and this should keep on happening, where W is n is the old value of the weight factor and this is the its updated value. So we'll consider following unconstrained optimization technique method to rely on the idea of iterative descent. So we'll go for three techniques. One is called method of steepest descent, which I just explained conceptually, which I'll do further. And the other is the Newton's method. And another approach is something called Gauss-Newton's method. So we'll see all this thing and we'll try to probe in that the pros and cons of each one. How do I go from one to another, and how do I know about this? So first one is method of steepest descent. So when I say method of steepest descent, so as I told you that this is basically to keep on each and every point you find a differentiation and you keep going down till you get the global minimum. So here successive adjustment applies to the weight factor. When I say this, so let me take a simple example which I forgot to explain here. Let's say this particular function was indicating f of x. So I'm talking about f of x here and x is here. This is the. So we want to find that value of x which maximizes this function, right? And for that, let's say we are finding, so a simple iterative ascending algorithm could be, I can write x plus 1 xn plus eta and let's say delta fx, whatever it may be, right? So it is finding here, and I can write, of course, that particular value of xn. Means what is happening? Initially, you start with some xn, and this is talking about the sample period, n0, n1, 2, 3, 4, 5, etc. So let's see if I'm talking about x0. So I'm approximating x1 next value, what it should be. Let's take n0 and eta and take the derivative and f of x0. I'll do this. So basically this is nothing but a first derivative. So what is this hell this eta is all about? So eta is all about, this is something called learning rate, or in order to that it is nothing but this particular spacing. Eta is nothing but the step difference between the two, you can say that. Always eta can have a value between 0 and 1. If it is too small, what will happen, that you are taking a baby step, small step you are taking. And if the eta is too large, what will happen, that it is too much, and there is a possibility that you may overshoot the global minima or global maxima. So accordingly, a trade-off should be done and it should be adjusted. Now this is regarding the gradient ascent. Now, and this is how you keep on doing this process. Now, question is, where do you stop it? When you stop, let's say, accordingly, you found x10. So this is x9 plus eta, whatever, and x9, you found this value. And how do you know that we have reached the point? And let's say, once you do this, fx10, of course, you'll be calculating the value, whatever there may be some alpha. And then you found that x9 some value beta, and there is a fx11, let's say there is some gamma. These are the value. I'm trying to give you some idea how this x will be related on when you come out of the loop, or you can say iterative approach. So when you find that, when you find it, because here you are gradient ascent you are talking about, so effectively alpha should be greater than any of these two, either beta and gamma. If that is the case, then you see I found the global maxima. But of course there is a another scenario, something called local maxima. If you reach, what is the problem, how to address that? Probably in your AI you might have learned something called shoulder technique, or shouldering effect happens, so that we'll see later. And that is from that one you can say it can happen. Now similarly, and analogous to that, I can have something like this. So I can have n plus 1 equal to xn. Now I'm talking about gradient descending. So instead of plus here, it is a minus, means you're going down. You're going down. And that's basically, it is something here. This is happening. And this process remains same. So instead of going up, you are going down. So this is gradient descending approach. Now let me come to this particular point. So we have this, as I mentioned this, uh, applied to the weight vector W in the direction of steepest descent, means you're coming down, that is in the direction opposite to the gradient vector. When I show the direction gradient opposite to a gradient vector, because gradient vector always point upward, so we have to go down, so we see negative across it. So we'll simply define this, say, just for sake of simplicity and as per the Haken's notation. I don't want to confuse you, because without notation also we can do that, but these notations make our life simple. So let's assume that G, we are denoting the nebula E by G. Okay, because instead of, why? Because later we'll be using delta. So everywhere if I use delta also, nebula also, sometimes you get confused. Because nebula is a differential operator, it is a gradient vector, and delta is just for indicating change, because just inversion of this becomes delta, right? So just to avoid this particular confusion, he has mentioned, he assumed that G equal to nebula E of W. That's all. Now using that, so steepest descent algorithm can be formally described as I mentioned earlier case, xn plus 1. So here is saying wn plus 1, that is a weight at n plus 1 iteration, that is nothing but the current weight, that is wn, minus eta that is the learning rate g of n, means same thing which I have explained you on the board, where eta is called the step size or learning rate of the parameter, right? So you know the what is the effect of this eta, we'll see further. So this is the technique of this gradient descent algorithm. This is how you do it, and this process you follow, and you'll be able to find the optimal value of W. Now this from iteration n to n plus 1 algorithm applies what of correction it applies, wn plus 1 minus wnify, right? That is a delta wn, it makes a correction. If I take this side, this is the correction, and that correction value is nothing but minus eta g of n. Okay, minus eta g of n. Just a minute. Okay, so this is the corrections you do, the corrections which you apply to the next value, and that when I do this kind of thing, so it may be negative, it may be positive. So every time you keep on doing this, so you are going down, down, further, down, down. Now let's see that we want to show that formulation, whatever we have discussed about, it really ensures that the energy, the error energy at the n+1 iteration is going to be lesser than the value of energy at W of n. Literally what I'm trying to say is something like this, saying that suppose this is Wn plus Wnth point, initial point, and this is Wn+1. So if we are saying that error here, the error energy here is higher than here. So I'm saying that at the ns+1 point, error energy is going to be lesser. So this is what we discussed that earlier. Means it is going to find in this way so that the next iterated value, the function value will be less as compared to the previous one. And this is what we want to try to show this. Now, how do I want to show it? We want to say that this kind of optimization or this kind of updation technique will help me that way. How do I show it? So let me talk about this. For this, we use a first order Taylor series around Wn to approximate the function. So, I hope this series, Taylor series, Maclaurin series, all this series has been taught to you in the first year. Even though it has not been taught, not a problem. I just tell you that what this series is all. So Taylor series is something like this. Is f of a, f of x basically, if you want to find across a. So this is f of a plus x minus a over 1 factorial f prime a plus x minus a whole square over 2 factorial f a double prime a plus keep on going doing. So in this case, we want to use Taylor series around W of n. Around W of n means this becomes our a. And to approximate EWN+1. So this becomes our x. Wn+1 becomes x. Instead of f, it is e, right? So we'll try to just expand this and see that when I write the Taylor series, how it look like. So as I mentioned here, what is x, what is a? So we are expanding this. So this, that is f of x equal to f of a, that is e of wn, plus x minus a, that is wn plus 1 minus wn over 1 factorial, and e prime wn. And we are ignoring the higher order terms. So I can write o of h. So ignoring the higher order term. So the question is that we are approximating using the first order only. First order means till the first derivative only. We are not going further. So we'll see that what repercussion it will have, that we'll see later. But first we want to ensure that whether this condition is met or not. How do I ensure this? Okay, so just a minute, let's see. This, when I do this, same thing we have written. Now instead of writing this I did for you to get comfortable with that. But actually I should written here nabla. When I say nabla, so it is I'm differentiating with respect to w, because w is not a one value, it's basically m-dimensional vector. Okay. And here I'm not writing higher order terms ignorance because it's obvious now we are taking first order derivative. Now when I do this, now here instead of nabla e, I can write g. Okay, I can write g. And this wn+1 minus wn, we can write delta wn, delta wn. That's why we use. Otherwise, here if a nabla also written and this also nabla and delta, you get confused. So this part has been written. Now, why I put g here? Now g is a vector because this is also vector, and the difference of two vectors is also vector because delta wn is also vector. Two vectors are there. Here there is nothing but simple multiplication between the two, which is nothing but the inner product. Now the question you may think, why you can't write delta t wn here? No, we normally don't write t on the delta here. It's we can do that over the bracket, but to avoid it, why to do this? If I simply can write g of t, only thing that t has to transpose has to be with the first vector, so that inner product condition is met. Okay, now let's see what we're going to do with this. So have you achieved anything? So just a minute, just a minute. Yeah. So as we have seen that delta Wn is minus eta g of n. From where I wrote this? So here, if you see, here we found that delta Wn is nothing but minus eta g of n. So using this here, this we can write E of w of n plus 1, that is f of x, equal to f of a, that is E of wn plus gtn. This is there, which becomes, because delta wn is in negation eta g of n, so I'll substitute here and it becomes something like this. Now here gt gn is there, is xt xn, which I can write as a Euclidean norm square without any problem. So this is given basically some value. Now you see eta n plus 1, eta n, so you can see that it's very clear now. Eta w of n plus 1 equal to E w of n minus this particular factor. Now what I'm trying to say that from whatever the previous state was there minus this particular factor, this value will be always lesser than the just E of wn alone. So it shows that E of wn plus 1 is going to be less than previous one. This is shown by this, and this is guaranteed and shown by this particular thing. Is there any confusion here? Anybody? Hello? This is very crucial because later with this concept, I'll be just popping up and invoking every now and then. And if this is not clear, it will be a problem at later point of time. Please clarify it if you have any doubt. So, no doubt. At least speak, one of you, so that I come to know, yes, you are listening, you are there. Fine. So no issues from my side. So we'll go ahead with this. So this is guaranteed. So this is using steepest descent method. Now we'll see that how it basically look graphically. So this is what, suppose there is something here and it has been calculated different values n, right? And small value of eta is there. Now and this is only two-dimensional vector, w1 and w2. Very simple, two-dimensional vectors are there. And this is how you are keep on finding. So a different kind of values gives. And this moment is basically quite smooth here. The moment from this value to the smooth, and this is going to the optimal value. But how do I know this? So just hold on for some time, I'll explain. So if the eta value is small, this movement finally getting the optimal value of w is smooth. You see the curve is coming smoothly. But when eta value is large, what will happen? This will having a zigzag variation. Sometimes it will go here, there, zigzag variation, which is not good, definitely. But finally, ultimately, it also find them. So this is a problem. So this learning rate value has a profound effect or influence on the convergence of the steepest. When I say convergence means you found that value of W, after which when you further change, it does not affect, the value remains same. So this means you have converged. If the value of eta is small, then system is overdamped and basically it gives me smooth trajectory. And when the value of eta is large, it's underdamped and it gives a zigzag or oscillatory behavior. Basically, this oscillatory behavior is not good in any way, but finally, ultimately, it solves the problem. So we'll see what can happen, because oscillations may cause overshooting the global minima. Possibility is there. And if it is too large, algorithms become unstable. When I say unstable means instead of finding the global minima, it overshoots and starts finding the other higher value. So this, which is I was showing now, you see that as if there is a basket, and from the top you're saying, you might have seen this in some movies, etc. This Assam tea plantations are there. So these ladies at the back, they will have a big basket kind of thing. So imagine that one which is nothing but it is the error space. And you starting from this and you're coming down, 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 and finally your objective is you see from the top of the basket, and this is the where the location you want to reach. So this is what indicating a contour plot from that perspective, how a gradient descent algorithm goes down. Okay, now with the problem, this the gradient descent algorithm is beautiful, no doubt about it. It's very simple, beautiful. It has been shown that yes, it meets the condition that next iteration next iteration the value of the function is lesser as compared to the previous one. So it's a good, fine. But the problem is here it's a like zigzag behavior is there, and that zigzag behavior, one of the reason may be that basically we have approximated using the first order Taylor series only. So it's what Newton suggested that what can happen. Of course, he didn't work in this aspect of LMS that time. LMS was not there, and so this Newton's method means the technique when we use second order Taylor series and to approximate the same thing, and we'll see that how this analysis is done. So basically, Newton's method is an extension of steepest descent, where second order term in the Taylor series expansion is used. So whatever we have done is same. Remember that x we are taking nothing but wn plus 1, a we are taking wn because we are saying that we are expanding Taylor series around a or around wn. Okay, and instead of f we have e of w of n. E is a function that is the error space, error function. So without going into further detail, I'm directly writing now f of x equal to f of a plus x minus a, f prime a plus x minus a square, f double prime. So this is straight. I'm using those words so that get confused. You won't get confused. E, and here this is f of a, etc. Now instead of writing this simple prime or double prime, you will be using in terms of nebula, because you know these are the vectors. These are the vectors now. So we have written the same here. So instead of first derivative, we say nabla, and here instead of second derivative, we say Laplacian, that is nabla square. So I have shown you also in the last class. This is a Laplacian operator. And see that slide in what is called matrix calculus. One slide I put it across. Now once you have this, so let's see this, what can be done and how do we go about it. So this can be written something like this. This minus this, that is EWN plus 1 minus E of WN. Can I write delta EWN means change in energy equal to this we saw already. This entire part can be written as GTN delta WN plus this half. 2 factorial is nothing but 2 into 1, so 2 only, so 1 by 2, and this here basically Wn minus Wn, and this becomes delta n delta W of n square. Remember this, delta is a vector. We cannot write a square of a vector, so we can write at max, if x is a vector, we cannot write x square, we can write xtx. So same way we have done here. So instead of writing this one at the same time wt wn, in order to meet the matrix calculation product possible, because here this is represented by a Laplacian matrix. This nabla square is a Hessian matrix which is denoted by h of n. So I can write delta wt entire part. Of course, the entire part I should mention, not wt. So remember that actually it is entire delta w and then over t hn. So this is the same thing we have translated here. Now let's see. As mentioned, this is basically a Hessian matrix. So Hessian matrix is denoted by this one. So dou square E by dou W1 square, dou square E by dou W1, W2, etc. So using this particular approach. And so let me revisit the same equation. So delta error energy equal to this one. Now we have to differentiate it. That we have to look into. So whatever I have calculated on taught you in my last class about the matrix calculus comes quite handy here, and we'll try to solve this one. Okay, we'll try to solve this how it has come to this one. How? So this we have to differentiate with respect to what? Delta Wn only. Okay, so let me write this equation on my sheet of paper, and then we'll start with this. So let me go to this. Let me write this. So we have, I have already written here. So this is my W of n, and here we have GTn delta Wn plus half delta W of n, of course the whole thing transpose, and H of n and delta W of n. This has to be differentiated with respect to delta Wfn. Ultimately, what we are looking for is we are finding the gradient of this factor with respect to delta W of n. So, order to avoid this confusion, I want to say this. So, let me write now this equal to Nebula entire part GTn delta Wn plus 1 by 2 delta W of n T H of n delta W of n. Okay. Now once I have this, because Nebula is a differentiator, it has linear operator, so it go one by one to this and to this. So we can write here delta, and of course in here I can write delta W of n with respect to what I am doing this. But if you don't write and say on the top, that is also sufficient. No need to mention everywhere. And 1 by 2 I can write it here, and sorry, it should be Nebula. Then this delta W of n whole T H of n delta W of n. So don't worry about this. It looks complicated. No, don't worry about it. I want to show you how it is looking like. This particular term is similar to delta x dtx. This particular term is similar to delta x xtax. So here remember that this is as per the formula we have shown you last class. This is nothing but just b. X here, c with respect to x means delta wn, xt hn, so hn is nothing but a matrix. This is x, so this is nothing but 2ax. Now you need not to write in exam something like this. This I am telling you for the sake of understanding. So here this entire part, because this is also GT, and you know that when it comes, actually it is something like this and T apply. So that's why it becomes B. So we just write here G of n transpose goes away plus 1 by 2 into, we can write 2a. A means H of n. X means delta W of n. And here this is whatever this Nebula is there. And now the job is very simple. G of n plus H of n delta W of n. I hope this is clear to you. Now I'll go back to the slide. Okay, just a minute. I'll complete this and then we'll disperse today. So we got this. Now I have to equate to 0, because normally it has happened. Finally, once you get the maxima minima, once you find the gradient, you equate to 0. Once we equate to 0, we get something like this, right? So delta Wn, so this becomes minus G of n, and this H goes, H is matrix, so H inverse Nga, right? So this is delta Wn value. Or you have only found the delta. So updation equation becomes something like this. Basically, it is Wn plus 1 equal to Wn plus delta Wn. From where it came? Nothing. It's a very straightforward. We always write that delta W of n is nothing but W of n plus 1 minus W of n. That's all. So we can say that at the next iteration, the value is nothing but W of n plus delta W of n. Simple. So this delta W of n we have already found, and which is nothing but minus h of inverse ngn, right? So once we have this, now in order for this to be possible, we have to ensure that inverse of this Hessian matrix always exists. This is the condition. So one thing is the good about Newton's method is that it converges quickly and does not exhibit the zigzag behavior which was very much inherent in case of the classical gradient descent method. But it has got its own problem. Newton's methods to work, we have to ensure that h of n, this one matrix, has to be positive definite matrix. Positive definite matrix is simple means inverse should exist, or it should be basically a non-singular matrix so that inverse can exist. And this I have already talked about: positive definite, positive negative definite, positive semi-definite. All these things I've talked in while reviewing the linear algebra. That's why I told that time. Also, the positive definite of Hn at every iteration cannot be guaranteed. This is the major problem with this Newton's method. It's very good. It converges fast. It's overcome the problem of zigzag, which is in case of gradient descent is there. But this is the problem. We cannot ensure that at every iteration h of n exists. We cannot say it is always going to be positive definite in this case. So we have to overcome this problem, and that we'll see the next when I talk about the Gauss-Newton's method. So probably that will take in the next class. Okay. So just hold on for a minute, and then I'll take your attendance and then we will leave.